Hi everyone, welcome back. So in this video, we'll go over how to create a basic PCell using IPKISS. So what we'll want to do in this video is we'll showcase the device we'll be using for this PCell, and then we'll add in some parameters that we can change that will adjust what the geometry looks like, and then we'll lay out the foundation framework of the code, and we can proceed from there into the next video. So to start off, we'll go into our Bragg folder here, and then we'll create a new Python file. I'll just call it demo here, so you guys can follow along. But you should have one that's completed called Bragg Straight already. And in here, we'll lay out the framework of the code first. So the framework of the code is quite simple. It's just a Python class. So we'll create a class, we'll call it Bragg Straight. And then the arguments we'll pass will be i3.pcell. And also we wanted to make sure we inputted our libraries correctly. So I'll take it from our previous videos script over there. We'll add it on top. So now i3 is inputted correctly. And then for now, we can just have nothing in here, just to kind of lay out the whole skeleton of the code. Under the class will be a second class called layout, with a capital L here. And in layout, we'll want to pass i3.layoutView. This is a library component from IPKISS, and it allows you to draw geometries from it. And it's also crucial for the remainder functionalities we'll showcase. There should also be a class called Netlist, and its arguments are i3.netlist from layout. And this is just here to access the netlist capabilities. It'll let you export a netlist from your device if it's connected in a circuit. So for this one, we could just write pass. And then what we'll want to do at the end of the whole script is add in a if underscore name underscore equal in quotations now underscore main. And what this does is it's a Python function that if this script is to be ran by itself directly, it'll execute whatever's under this section. Otherwise, if it's inputted, it'll just ignore this section and won't run the script here. So it's a great way to debug your code. And we'll just leave it for now and write pass. So what we'll want to do next is, let's go through the device we're going to make today. So the device we're going to make is a straight Bragg grating waveguide. It's a waveguide with a bunch of small gratings along its length that will create a filter response. So I think this is a great device to practice PCell and scripting on, simply because it has these periodic gratings over here that allow you to create loops. So it's a great initial exercise in first creating the basic shape and then adding more complexity and then finally creating loops on top of that. So what we'll want to do today is we'll first create the waveguide. So we'll have some parameter called waveguide width over here. And then we'll want to create the gratings. So each grating is calculated based on its period. So that includes the grating itself and this little air gap on the right over here. Let's see if I can zoom in here. So this is the period, period loosely here. The next thing we want to care about is we want to care about the corrugation width, which is how deep these gratings are drawn. And the definition of this corrugation width is, the convention I'll go with is to pick the center point as the waveguide's width. So if it's like this, this would be the waveguide's width, lengthwise like that. And then define it outwards and inwards. So this whole thing is called DW in the convention that I'm familiar with. So we'll want to take this whole grating width as DW. And then next we'll want to know the duty cycle or fill factor. So in this period, how much of it is the grating and how much of it is the air. So right here we have 50%, and we'll take that as our default value. And then the last variable we'll care about is how many periods are we going to draw. And then this number will also determine how long the device length is. So coming back to our code now, what we'll do is under class, we'll indent, and we can start adding our parameters. IPKISS makes this quite easy to do. It has some predefined variable classes that help you not only debug the value you put in, it also can help designers hint at what might be a correct parameter and what isn't. So what we'll do first is we'll create a variable called _name_prefix. This is just the internal name that the device will be called, and then we'll call it Bragg Straight. Next, we'll also add something called a trace template. This is used by IPKISS for the circuit-sided functions. We won't talk too deeply about this. There's plenty of documentation online for it, but we'll keep this in place because we want to showcase some features later on. So this one, we can just leave a small note to ourselves called trace template of the access waveguide. So this doc right here is a documentation notation, and then you can leave a string for yourself. So underneath that, we'll make the actual parameters now. We'll create parameters here as a little note to us, and then we'll start with the period. So the period, ideally, we want it to be a positive number. It can be a decimal. So we'll use the type provided by IPKISS called positive number property. And then we can set a default by passing a default argument, and we'll just say it's 0.32. Then in the documentation, we will add a note. We'll give a description. It is a distance between a set of gratings, and we can also leave our units. So it will be microns in this case. Next, we'll do the period number. So this will ideally be an integer. You won't really go into negatives. You won't have decimal points. So we'll do IPKISS, and then IPKISS has a positive int property. And with that, we'll pass a default of 100. Let's say it's 100 gratings long. And then we'll also leave ourselves a note here, amount of periods. Next, we'll do the corrugation width. So dw equals I3. And this time, we'll pick a non-negative number property. And the reason for this is we could reuse this PCell as a waveguide. If we set this dw to 0, then no corrugations will protrude from the waveguide itself. And essentially, you could use this as a kind of double feature PCell. So here, we'll set the default to 0.04. And the documentation will say it's corrugation width. And then we'll leave a unit over there of microns. Next, we'll do duty cycle. And this will also be a non-negative number. So the reasoning is because this will just be a ratio from 0 to 1. We'll default it at 0.5 for 50% of it being grating, 50% of it being air. And then the comment here we can leave is ratio of grating versus spacing in a period. And then we can tell us it's 0 to 1 fraction. Next, we'll add the waveguide width. So we'll do waveguide underscore width. And this will be the same property as the period. So it'll be a positive number property. The default, we can set it to 0.5. And the description, we can write waveguide width. And then next, we'll add a special property for SWGs. So SWG stands for sub-wavelength gratings. In sub-wavelength gratings, there's a scenario where you might not want to draw the waveguide. You might want to hide it like so. And we want to add this feature here. And it can just be a Boolean. It could be something very simple as true or false. And we'll decide if we draw our waveguide from that or not. So we'll do I3, and we'll pick the Boolean property. We'll set the default to false since we want to draw a straight waveguide, Bragg grating in this case, not a sub-wavelength grating. And then we can give ourselves a little note that says enable to remove center fishbone spine. So some designers might refer to this center waveguide as a fishbone spine. So that's why we use this notation here. So with that, we also want to add in some layer properties. So what layer to draw our device on. The first one will be a device layer. We'll use the IPKISS layer property for this. And the default will be the PDK's ec, and then we'll do pplayer.si. This is just the default layer for that PDK I'm using. You can set it to any layer property you wish. Then we'll just say layer for the device. And then we'll do the same for the cladding and the cladding layer. So here, we'll just add the two. So the cladding is a Boolean property. We'll add it if you want cladding. If you don't want cladding, we'll set it to false. Otherwise, if it's true, we'll draw it on the cladding layer. In this case, it's si_cladding for this PDK. And the reason why we add this here is because there'll be a scenario in the next few videos where we're going to create a geometry for the simulation. And the simulation doesn't have to be the full device length. You can take a segment of the simulation to make it smaller, and then it's more efficient to run. And the results will not differ much than the full simulation itself. So with all that there, our code's set up, and we'll meet each other in the next video. Thanks.